solving all the world's energy problems once and forever.
Good morning, Genesis Academy.
Good morning, Dr. Noel.
Happy New Year.
Happy New Year.
Okay, so we have a very special presentation for you today. Dr. Peter Schubert has a PhD from Purdue University. He is also a licensed professional engineer and a distinguished professor emeritus. Dr. Schubert holds over 50 patents and has published more than 120 technical works, including 2 textbooks. He has received awards from the U.S. Department of Energy, Agriculture and Science, and Defense, totaling more than $5 million. Peter has been a vegan for 36 years and is happily married to a Bahamian girl at the back who may never become a vegan. Let's give a round of applause for Dr. Peter Schubert. Yes, she is also a retired elementary teacher. Okay, so let's give Dr. Schubert another round of applause.
Thank you all so much. I'm really excited to be here. Pastor Hannah's been trying to get me to speak to students here for about 5 years, so it's finally happening today. What I'd like to talk to you about is solving all the world's energy problems for once and forever. At your age, you're probably aware that there's a climate crisis that's happening across the globe, that we're trying to get away from fossil fuels, trying to reduce the carbon in the atmosphere, but yet it seems to the problem keeps getting worse. We're not finding a way to find that solution. So what I want to show to you today is a positive message for how that might be accomplished, and it might be a way that you could make a difference in that as well. Next slide. In addition to the stuff you heard on the bio, just this morning I got please forgive me. I was just announced as a visiting professor at Newcastle University, which is in the northeast of England. I visited there a couple of times and gave a presentation to their college students and professors that was similar to what we're talking about here, and they were so excited they said, "We'd like you to be a visiting professor at our university." Next slide. There's a lot of information on this, but I'm going to summarize this, and the last slide will show this as well. If we're trying to solve energy, not everybody fits in the same category. So I've grouped this into 3 areas. One is urban areas. Think of Nassau and New Providence. The other one is rural areas. Think of, down in the middle part of the island. And then the third part is mobility and transport. We need to be able to move ourselves and goods from here to there. So these are the 3 areas that we need solutions for clean energy. And what you see in some of the small pictures, I'll go into a little bit more elaboration as we go on. For rural areas, and this includes sub-Saharan Africa, this includes many of the nations in Southeast Asia, this includes many areas in South America, as well as rural communities across the United States, where they're not connected to a city, but they need to be able to use resources to be able to do their work as farmers and providing food. Now, I'm not only interested in how we do this in those areas on Earth, but I'm also thinking ahead to when we have facilities on the surface of the moon or in orbit around the Earth or even beyond. So a lot of the work that I'm doing starts with where we are now in 2025 and thinks ahead to where we'll be when you are all my age and we have habitats on the moon. How do you grow food there? How do you take care of your waste? How can we turn our waste into energy in a local facility? So it's all about using resources that you have locally so you don't have supply chains that reach across the earth. You're not drawing petroleum that's mined in certain places then shipped all over the world. We're trying to make everything local and distributed rather than centralized and controlled by large corporations. Next slide. This block diagram shows a concept for a village in Southeast Asia that grows rice. When you grow rice, it comes with a very hard husk on the outer edge. So in order to get the part inside that your body can digest, you have to dehull that rice. Those rice hulls are, oh, thank you so much, are very hard to break down. They don't burn well because there's a high sand content inside that material. So we would like to turn that into energy, which is currently a nuisance, a waste. So in this approach, we can take these rice hulls, and there's mounds and mounds of these on the rural roads in Southeast Asia. Think of Thailand and Cambodia. And we can turn those through a gasifier into hydrogen electricity. And in addition to those, we can also produce fuels for vehicles. So if a farmer makes more rice than they need for their family to consume, they can have the mobility to take it to a market and then sell it at the market. So they can become part of the market economy and increase their standard of living. At the same time, we can also make electricity. So the electricity can be used for education. Many times these rural communities have very little access to education like you guys have here. So if we can provide that through a screen even and a connection to satellites, we can connect these people who never get a chance to get an education to the best teachers in the world. So this is a way that takes the 1.2 billion people on this planet who don't have access to electricity, who don't have access to education, who live a subsistence farming life, and help to raise their standard of living in a way that uses local resources so they're not increasing the burden on the planet. Next slide, please. This is a picture of the first gasifier that we made for use on a farm. We called it the Freedom Farm. And this machine would take corn stover. So you know when corn or maize grows, it's maybe this tall, and there's 2 or 3 cobs, and the grain on there is what goes to market. So that turns into grits, that turns into cornstarch, that turns into corn on the cob. But all the rest of that plant, the stalk, the husks, the cob itself, and the leaves, all that is a waste material. And that just gets dumped on the ground and sometimes burned. So our idea was to be able to take all that material and gather that on a farm and then have the farmers use that to produce their own electricity instead of getting it from a coal-fired power plant many miles away. We could use that to make hydrogen that they can use in fuel cell tractors to go do the passes across the land that they need to do. And then we also found that we make biochar. Biochar is when you have a form of carbon that will stay in the soil. It'll help the soil absorb water. It'll help the roots of the plant grow through the soil more easily. And it also provides a place for nitrogen-fixing bacteria to grow, and the nitrogen is what goes into the plants, and that makes the protein that we need in our bodies. So this biochar is actually a way that carbon is taken out of the atmosphere by the corn as it's growing, and then after we turn that waste, the corn stover is a waste, after we turn that waste into energy and fuels, we're left over with a biochar. It's a waste of a waste, but it makes carbon negative. It means we've taken carbon from the atmosphere and now we can put it into the soil where it stays forever. It's a permanent biochar. This is so much more efficient than the way farmers do things now, where they run their tractors on diesel fuel and they put fertilizer on their crops that's made from petroleum also. Next slide. When we treat the corn stover, we turn it first into a gas. The gas is a mix of carbon monoxide, not good for people, but it's a good fuel, and hydrogen. So this mix of hydrogen and carbon monoxide, we got an award from the US Department of Energy to figure out how to extract a pure green hydrogen from that. Green hydrogen is of great interest to many corporations for sustainable aviation fuel. As you guys see the planes that are coming and going in your airport and going across the sky above you, what you're seeing mostly is the water vapor. But what you can't see is the carbon dioxide that's left up in the upper atmosphere from all those airplanes. So almost all airlines want to be lower carbon. Instead of getting their fuel from fossil fuels, they want to get it from plants. But they need hydrogen, and they need that hydrogen to be green. We told the United States government that we could make our hydrogen for less than this is the $1 line. We can make our hydrogen for less than $1 and a carbon score of 0.36. The current way of getting hydrogen is from methane or natural gas. That has a cost of $3 and it has a carbon score of 9. So we're 3 times cheaper in price and 25 times lower in carbon intensity to make the same hydrogen. This is so green, this meets the United States goals for 2030 5 years early. And yet, my small company can't get people's attention on this. I'll come back to that point later. Then to store the hydrogen. Hydrogen is very difficult to store. It's a very small molecule. It will leak out of almost anything. So you either have to have a very expensive tank, or the approach we're using is a solid material based on silicon. Silicon is the part of sand. Sand is silicon and oxygen together. So if we separate those two and take just the silicon, that's the same stuff used in solar panels and in integrated circuits. We found a way to use this to store hydrogen. This is a picture magnified so that the width of your hair, the thickness of your hair, would be 50 times this width. So all those surface areas can store hydrogen. We have 4 patents on this technology. This is a way that the farmers can create the hydrogen from their corn stover, and then we can store it to be able to use on their vehicles so they can drive it around. Next slide. And then the ultimate approach to serving cities, and most of the world is moving towards cities. Cities are 70% of the world's population, and they require power plants from all sides to deliver them power, usually with a mix of natural gas and coal and nuclear. The approach I'm pursuing, and I didn't invent this, but I am the one who figured out how to make this economical, is to put solar panels in orbit. Now, you probably know that the space station orbits around the Earth and it's in darkness half of every 90 minutes of its orbit. But at a higher orbit, the shadow of the Earth is tiny, so these will be exposed to the sun except for in the spring and summer for a couple of hours, 24 hours a day. Now, the challenge is, how do you beam that power back to the Earth without heating up the atmosphere or messing up electronics? And so I figured out how to make a beam of power which is not concentrated, could never be used as a weapon, but it can now deliver power so that one of these satellites could serve all of New Providence as well as the surrounding islands. So one of these satellites will provide 24-hour power to the nation of the Bahamas. It starts with a factory that I've got 3 patents on for how to extract the silicon from the lunar soil, which is 21% silicon. This is an AI-generated image of a young lady working in space to deliver power back to the Earth. Next slide. These are some of the students I worked with as a professor. I took an early retirement in July, but I had each of these students has been involved in publications where they are working on cutting-edge research for hydrogen storage and wind turbines and biomass gasifiers, and we published this work, and they all got great jobs because they did research as undergraduates in our university. Next slide. I also got a grant of $100,000 in 2023 and worked with this group. This is Yvette, who's in the back. But Sister Claire here was my main partner. She just turned 95 years old. She and I put together a team that helped to do energizing rural communities. In a small community in southeast Indiana, we helped to raise the awareness of the importance of solar energy and wind and biomass for people who are sometimes told that stuff's bad for you. Solar panels will leach poisons into the ground. They'll take away farmland from production. Food prices will rise. There's a lot of disinformation in the United States about those topics, and we set the record straight on those by giving people good information that they could go and confirm. Next slide. So this is the overall view of, at the top you see the baseload power coming from space. Over here, portable and mobile power from hydrogen. And this can be used, for example, in trucks. Now, you guys see trucks every single day. Those heavy trucks, if we were to convert them from diesel fuel to batteries, the batteries are so incredibly heavy that the roads would be tore up even more than they already are. So batteries are not a solution for long-distance trucking. But hydrogen can be stored 9 times more efficiently than batteries. So batteries are okay, but hydrogen is the ultimate way for transportation. And then for local areas, and this includes cities, but for rural communities, they can use their local biomass to provide the electricity, the heat, and the fuels that they need to do their operations, as well as taking carbon out of the atmosphere and reducing the carbon that we put in there as a species by burning fossil fuels. So to summarize, Now I want to take a diversion because, as I mentioned earlier, I'm having a hard time getting people to pay attention to this in the United States, and also in Europe, and also in Japan. I believe that these are breakthrough technologies that can help everyone. But there's a great deal of resistance to new approaches to energy. The U.S. Department of State sent me to the island nation of Malta. Malta has many similarities to the Bahamas. They have about 400,000 people. They are a 13-mile long island instead of 22 miles long. They have a deep port where they get 1.2 million visitors per year. They have a parliamentary system because they're a former colony of the British nation. And when the United States sent me there, they said there's 2 huge problems they've got. One is they have a big power plant that's burning bunker fuel, which is the cheapest but also the dirtiest fossil fuel there is, similar to what you have at Clifton Point. And also they had a landfill that had filled up faster than they thought it would. So then they built a bigger landfill, and that one was getting filled up faster than they thought it would as well because of what the people were generating as trash and all the trash that came in from all their tourists. So they said, Dr. Schubert, can you go there and help them? So I spoke to many different groups during the time I was in Malta to say, if we take that waste and turn that into energy, that solves 2 big problems at the same time. Because those power plants send pollution out over the sea. And the trash gets leached out and it goes down into their drinking water, which they don't have very much of. So if they can convert their trash into energy, then they can have less of the bunker fuel and less of their landfills. But what I found out was that their government was always decided between 2 parties by 1% of the vote, and the party that was in power at the time was afraid of doing anything that might be risky or that might overstep the budget, because then the other party would criticize them and then the elections would go back the other way. So both parties, once they got in power, were afraid to do anything different. So they are stuck in their old ways of doing things and unable to make any kind of change. So in order to address that, let's go to the next slide. I developed a book for how to create a corruption-resistant government that is fair and equitable to the people. So even though almost all of my work has been in the physical sciences, this book is a manual, a how-to manual for countries that need a better form of governance that won't be controlled by the large energy companies, because energy companies make a lot of money and that gives them a lot of political influence. So I'm trying to look at a comprehensive approach to doing smarter things with energy that help everybody and not just have the rich get richer. So final slide. So to summarize, there are innovations. I've got some. There are other people around the world who are coming up with smart ideas. We need young people like you to use your minds to figure out not just the technology, but also the policy and the finance. These are very multidisciplinary, very diverse problems, and they're very hard to solve. So it's extremely important to me that our young generation, each of you, find a place in your life where you can help work in solving these problems for the future of all humanity. So with that, I would very much welcome any questions that you might have from my talk. Thank you for your attention. Pastor Hannah.
Dr. Schubert,
be a little easier. Yes, sir. Have I ever been to the moon? My role is to send young people like yourself to the moon. So I come up with the factories, and then you take them to the moon and operate them. And then that way I don't put myself at risk. I'm terrified of getting into space because it's so dangerous and risky. And I feel that the strongest benefit I can make is to figure out the solutions, the hard problems, and then have young, able-bodied people go out there and be able to do that. Thank you for your question. In the back.
So it's sound like you're thinking of carving the island revolvers. How big do you think that it's an estimate of how big do you think the satellite should be?
How big make which?
The satellite you spoke of that could power the Bahamas, how big a satellite would that be?
Yeah. How big does a satellite need to be for space solar power? The answer is really big. We've built much larger. Kilometers. And it's so big because sunlight is really spread out. So when we had the factory on the moon, I showed just the first step of that, but I had students work on the design for an entire lunar base that would be near the lunar South Pole that would process silicon into solar panels, launch those into orbit, and then another group of students worked on how to assemble that into one of these, I call them a tin can approach. So it would be 6 kilometers from top to bottom and 6 kilometers in diameter. So it's a truly huge structure in space. And then the transmit antenna is 1 kilometer in diameter, so very big, would cover the entire downtown Nassau. And then the reason why that needs to be so big is so that the energy coming down is not too concentrated, because if you use it too concentrated, that makes it easier to turn into a weapon, and I want to very strictly avoid any kind of technology that can be used as a weapon. So we're choosing specifically technologies that will always be used for good.
It's almost 4 miles wide, like 4 miles.
Yes.
I was taking a few notes, so you mentioned having a lunar base. Did you say that you were trying to extract carbon or hydrogen from the moon's surface to power the plants? And then I have a follow-up question after that.
Yeah, for the questions about the lunar base is, are we just extracting carbon or hydrogen from the moon? Carbon is almost absent from the moon. Hydrogen is almost absent from the moon, so we don't get any of that. So on the moon, you've got silicon, oxygen, titanium, aluminum, and iron. So my patent is how to extract all of those simultaneously. So what we can get is the silicon that we can turn into a crystal and then use that to make the solar panel. So oxygen we can make, so you need that, of course, to breathe. But carbon, all the carbon will have to come from Earth or possibly from an asteroid. So I've published 3 science fiction books, and in those books I explain a technology for how to harvest the carbon from the asteroids to be able to provide that to the moon.
So my follow-up question was, I'm aware that helium-3 is abundant on the moon's surface. Have you considered using that for nuclear fusion in the production of power for this idea? I mean, I know you're primarily focusing on biomass, but since you started talking about working on the moon, have you considered using helium-3?
Yeah, so the question is using helium-3 from the moon. This is a technology that the Russians are very excited to go try. There's been 2 movies that I know of that use this as a plot device. So I had my students look into the helium-3. The sun is always spitting out, light and energy and helium-3. So some of that impacts onto the surface of the moon and gets stuck there. So the idea is if you can gather up enough dust, heat it just a little bit, there you go, there's your helium-3. So we did a study to say, how big would that factory need to be? Not very big, but we have to launch it to the moon, we have to land it safely on the moon, we have to have robots to operate it, then you have to have a way to go harvest a lot of it because it's spread out. It's not deep, so you have to travel across distance. And we found that the amount of helium-3, even using the most optimistic estimates, was not enough to justify the expense to get there. We found that we could get maybe a profit back on Earth, but it would be pretty small compared to the amount of expense. It would make really great nuclear fusion. And nuclear fusion is what got me excited about going into science and technology in the first place. So I know like a lot about fusion and about fission, and it took me a long time to let go of that idea of helium-3 because the data was telling me, no, Peter, it's going to be the silicon and the solar light that is going to be the most cost-effective. Good question. Yes, sir.
How would you how do you send it to space if it's like so big, like the satellites? How would you send it to space when it's big?
Yeah, the question is how to send the materials from the moon up to the satellite if it's 4 miles across. You can't do it in one go, so it's got to be modular. So each of the panels would actually be relatively small. You've seen the ones that are on the roofs of buildings around here. These would be smaller than that. And then we have to put them inside of a cannonball. So we're going to make a cannonball. It's actually just a shell of iron, and then the silicon gets packed inside of that. And once we've got it inside of iron, we put it into a giant electromagnet, and we accelerate it in what's called a Gauss gun. So you have a series of circular magnets in a line, and you turn on the first one, and your cannonball gets sucked towards it. But before it gets there, you turn it off and turn on the next one, and so it keeps getting sucked forward. So you can accelerate them really rapidly and then launch them into space. And then another of my patents is how to receive that in orbit. Because if you have a cannonball coming at you, it's like, how do you slow it down in space? You don't have anywhere solid to push onto. So we use electromagnetics to also slow it down. Once we have those, then we have to crack them open like an egg, take out the solar panels, and start stitching them together. So we can also get aluminum on the moon, and we use that for the framework to hold the panels together. Great question. Yes, ma'am?
So you send people up there to like build them while they're in space?
Yeah, so the question is, do we send people up there to build them? There's a big debate in the space community whether to send people or robots. I love the idea of sending people. And in my science fiction books, it's people that do all the work. I think that's the right way to go. But if you think about people, we have to send all the food they need. We have to send all the oxygen they need. We need to send a big enough space for them to move around in. We have to take care of their wastes, if you know what I mean, their bodily wastes, and process that. We have to keep a controlled environment. We have to protect them from the radiation that's coming from deep space. You know, we're inside the Earth, and we've got the whole thickness of our atmosphere to protect us from cosmic rays. But once you get outside of the Earth's atmosphere, you're exposed to a lot of radiation. And if you don't have good protection, you'll get leukemia very quickly. So we have to have shielding for that. So when you add up all this stuff needed to take people into space, it's like, well, robots are a lot smaller and cheaper, and they're replaceable. Leukemia is a cancer of the blood, and it's one of the reasons why no one's gone to Mars yet, because it's a 6 to 9 month duration just to get there, and the exposure that you would get based on data that we take on Earth says you'd have a 50% chance of leukemia by the time you get there, and if you even want to come back to the Earth, it's game over. So space is very, very dangerous. That's why we think about robots. You had your hand up earlier. Yes, please.
So, you build the satellites in space, yes? So, what happens if you built most of it, but it gets damaged somehow and it's unfixable? What do you do with the materials afterwards?
All right, so we got a really hard question here. I'm sweating now. What happens if the satellites get damaged? What do you do with the materials? So there's two aspects to that, or three. One is, what if you have bad actors from a rival state that say, we don't like it that you're getting this free power from space, and they attack it? There's almost no way to prevent an attack. So that's why it's really important that this be something that can be provided to everybody on Earth. Another one is debris from micrometeorites. So micrometeorites are flying through space. The space station gets hit all the time. Most of them are pretty small, but those will definitely take out the solar panel that they hit. So we have a concept for having robots that will they'll be like spiders that crawl along and test each panel, and they have excess ones on their back, so that if they find a bad one, they replace that with a good one and then take that back to the depot. The third part of your question is this will last for about 45 years in space, but we have to do something with it when we are done, when the solar panels are all used up, because they get exposed to the radiation of the sun, and that causes them to get slowly damaged. So the orbit we'll use is called geostationary orbit, where it goes around the Earth at the same speed as the Earth rotates, so it looks like it's hanging in the sky. But there's a graveyard orbit that's 2,000 kilometers higher up than that, where people have routinely been putting satellites that are no longer working to keep them out of the way of the ones in this special orbit. So that's a possibility. The ultimate answer would be if we could power it and just send it into the sun won't care, it's completely safe and harmless, and that gets it out of the Earth's orbit entirely. Good question.
One more question.
Okay.
Sorry. How long do those take to build?
How long does it take to build these satellites? We looked at a very aggressive time frame. If you had everything all figured out in advance, a huge team of people, like everybody in this room, all working on different aspects of this hard problem, and then we had the robots could do it in 3 years. In reality, everything always takes at least 3 times longer than I expect. So maybe 9 years. Yes, ma'am.
How long would you say it takes to get everyone ready to go to space and to also launch the satellites, like all of that together? How long would that take?
Yeah, the question is, how long does it take to get people ready to go into space and get the satellites ready? For getting the people ready for space, we have a small astronaut program in the U.S. The one thing the U.S. is doing is to make sure they have the highest trained astronauts to take care of any situation, and they're very valuable, so much so that NASA says we will accept no risk. We don't want to put our astronauts at risk. So it may come to pass that we need more astronauts, and to realize that just like with many other large and important building projects, there may be some loss of life. It's my opinion that we have to get past the attitude that there can't be any risk. There should be a small risk, but there should be a high reward. So that's a policy issue, okay, for getting the astronauts ready. And in my science fiction books, I talk about how we get students like that would be saying, I'd take a risk if you're going to give me $1 million and there's a 1 in 25 chance I might die. Some people might say, okay. In terms of getting the satellites ready, that's what we call non-recurring engineering. That's the design work that needs to happen for this to go ahead. Over my career of about 30 years, I've had maybe 700 students work for me, and I tell them all the same thing. And I'm going to tell you and all of you now today. This is going to happen at some point. Humanity is going to reach a point where we say, what we've been trying to do is not working. We need smarter ideas. And they're going to discover Dr. Peter Schubert, and they're going to say, what will it take to save the Earth? And I'll say, I want $100 billion, and I want to be on every television on the planet. So I'm going to call back all those students that I told, what you're working on now is a small piece of an overall complex project. Go out and get jobs and learn all the skills that we'll need. And when you see me on television, and I say, all right, come on back, let's do it, then I think we can get it done in just a couple of years. Thank you for your question. And back here?
Gathering all the materials to build the satellite, how much would all of that cost?
Our question is, for gathering the materials for the satellite, how much would that cost? The materials on the surface of the moon are free. There's an outer space treaty and a moon treaty that say the moon belongs to all of humankind. So we don't have to pay anybody to mine the moon. We do have to get rockets there, and either the people or the robots to operate them. And that's where the big expense comes in. So the work that SpaceX is doing is reducing the cost of launch into orbit. But still, that's just the orbit around the Earth. Getting to the moon is not too much more expensive, but then landing on the moon takes a lot of fuel. So you have to launch all that fuel and then take it and then use it to land. And then if you want to get back up, you've got to carry that with you as well. So the rocket equation says that the more stuff you want to get out there, you have to have a much bigger rocket over here. So that means that you are really constrained to get the lightest possible mass of your apparatus. And if you can get a light mass there, then it's not too terribly expensive to get it there. And then the cost is free to operate because you can use sunlight as your power source. So it all has to do with launch mass. So the most important thing is getting that launch mass down. And when we do our estimates, we say for getting one of those satellites at 5 gigawatts, all told, including the lunar base, that the amount of money we need is $16 billion. Now, if we compare that to a nuclear power plant that also does 5 gigawatts, those cost $25 billion. So it's a huge investment, but it's cheaper than nuclear power plants and way safer. Yes, sir.
How long do you think it will take until climate change is unfixable?
The question is, how long will it take before climate change is unfixable? It's already happened. Here's the reason why. Methane is 25 times worse for global warming than carbon dioxide, but it also comes out of the atmosphere pretty fast. But the carbon dioxide that we put into the atmosphere, we've seen our temperatures go up by 1.5 degrees so far, Celsius. Once we get to 2.0 degrees, that's when really bad things start to happen. The amount of carbon we put into the atmosphere takes a while before that shows up in the heat. So we're already 10 years, we're only feeling the effects of 10 years ago carbon. When COVID hit, carbon emissions dropped way down. Everybody's like, yay! And then as soon as COVID was over, it came back up and everyone's like, oh. So our globally, the graph of our carbon over time took a dip during COVID, but then continued on the same increase that it was on before. So even the United Nations doesn't model that scenario. They're assuming sooner or later we'll do something about this, but it hasn't happened yet. So it's my opinion that it's already too late. And that's why all the things I'm working on, I'm patenting them, I'm publishing them to make sure that there's a record of how to fix these problems so that when humanity as a collective whole wakes up and says, we have got to do something different, that they'll say, who's figured it out? And as I mentioned before, I've been systematically working on the hardest problems, but knowing that I probably won't get to do them before a crisis hits. And then the question of how long will it take becomes super important. So I tell my students this, figure out how it's done, teach others how to do it so that when we really need it, you've already figured it out and can give people a jump start in solving these problems. Yes, ma'am.
So you said satellite could span across the entire Bahamas. Would it span any further? Like, would it reach any other places?
Yeah, the question is, could the satellite serve all the Bahamas and how far could it reach? As a case in point, consider Malaysia, which is on the other side of the earth, but it's similar latitude. In Malaysia, their land is not really available for one of these antennas, but they have a strait, the Strait of Malacca, where this could be done that doesn't affect shipping lanes. So we could actually float the receiving antenna, which has to be 10 kilometers in diameter, it's 6.1 miles, and float it there and then send the power down there, and then that could be now taken with a cable and then power Kuala Lumpur, which is a very big city. So what we'd probably do in the Bahamas is find an area that's not important for shipping, it's not important for fishing, and then put this where it's going to float on the surface, so it's not going to affect marine wildlife, but it means you can't drive ships through there. And then it's only limited from there to cables. So amongst the 700 islands of the Bahamas, we could probably reach the big ones, but not all of them. That's why we have this other approach of using the biomass to use local resources for when you're not close enough to a city to get the big power. Thank you. Yes?
I saw something and it was like people when they go in space
Yeah, this actually came from Albert Einstein. So special relativity tells us that if you move faster, closer to the speed of light, time slows down for you. So if you have two twins, same age, and you send one out on a rocket ship close to the speed of light, and then they come back, the twin that left and came back may have aged 1 year, but the other one may be aged 10 years. So they look like father and son. So in space around the Earth, there is a small amount of time, what's called time dilation. So astronauts in orbit experience time at a different rate than we do on Earth, but it's pretty tiny because they're not moving very close to the speed of light, which is really, really fast. So it's true, but not big. Twice I have been ready to speak at a conference, and Elon Musk came and said, "I'm going to speak," and then they said, "Dr. Schubert, you're canceled." He wants to go to the Mars, I want to go to the moon. He wants to do batteries, I want to do hydrogen. So I want to solve the world's problems with space solar power. He says it's too inefficient, what a dumb idea. So he and I are on the opposite ends of all technologies. So I don't care to ever meet him. Yes?
Due to the lack of oxygen in space, even with the air tanks, will it still be hard to breathe?
Yeah, the question is, due to lack of oxygen in space, even with air tanks, it will be hard to breathe. If your breathing apparatus runs out of air, it's just like being on a scuba dive. You're toast. If your suit gets hit by a micrometeorite and has a hole in it, and all your air leaves, then your body is exposed to a vacuum. And what happens is that your blood will boil out of your pores, and your eyes will pop, and you will puff up, and it's a very horrible way to die.
How long does it take for the air to run out without the suit popping?
It depends on how you design it. Any final questions before we wrap up for the day? Yes, sir.
Would it be possible to a giant electromagnet to catch asteroids and use materials from asteroids to conserve energy? Would that be possible?
The question is, asteroids have minerals, right? Can we use giant electromagnets to catch them? Yes. In fact, I wasn't going to talk about this, but they also have platinum. So platinum, gold, iridium, those are called platinum group metals, and those are found in metal-type asteroids. And I'm in the process of publishing a paper on how to get a rocket out to the main belt asteroids beyond the orbit of Mars and gather $1 billion of platinum, which is a cube about 1.5 meters on a side, and bring that back to Earth. And that one does make money. So a lot of high net worth individuals have been interested to go harvest platinum from asteroids, and then they're like, oh, nobody's figured out how to do that, so I figured out how to do that. So that may be the first thing that happens with all this stuff, and if people won't buy my green energy technologies, maybe they'll pay me to get some platinum for them, and I can use those profits to develop my biomass technologies. All right, that's my whole plan. Thanks, everybody, for your attention today.
Dr. Schubert, on behalf of the principal and administration of Genesis Academy, I would like to thank you so much for your presentation. It was very interesting, and it gave us a lot to think about. Students, I hope you realize that this is why we have a STEM program here at Genesis. This is why we have our strong science program here at Genesis, and we have your STEM and your sciences teachers in here for this very reason. The reason you are learning engineering is so that you can think about ways to solve some of these problems. And here you were able to meet an engineer who is currently in the process of solving these problems. And as evidenced by some of your questions, it seems as if you were making the connections, Ms. Wilkinson, from those classes, especially on engineering, that had your mind ticking and asking these questions. And so if you are wondering, who is solving these problems in the world, you get to meet somebody who is solving some of these problems in the world. And even greater is the fact that he's saying that you have the ability to be problem solvers as well. When you come to Genesis, this is the place where great minds begin. We don't want you thinking, oh, I go to a small school and I come from a small country, and so my ideas and my talent is small. No, God gave you unique talents and intelligence, and we are here to help you develop them, to think deeper as to how to solve some of these problems. And guess what? A lot of the problems with global warming and climate change is affecting your very country. So you need to be especially alert and especially concerned, because the bigger countries don't have the same concerns that we do. They don't have category 5+ hurricanes threatening them every year. They don't have the thought of tsunamis taking over their entire country every year. They don't have BPL to deal with every day, okay? And so I know that the whole idea about the satellite providing consistent power especially was interest to these students here, because they experience day to day the challenges that we have with reliable, clean energy. So let's just give Dr. Schubert another round of applause.